This lecture is a further discussion of motion of a charged particle in a magnetic field. We already have the equation that force equals QVB. Okay, so this is the force on a moving charged particle. So it's force, and then this is the charge, the moving, so it has a velocity in a magnetic field. Okay, so what if we send a particle through a magnetic field that is going into the board? Okay, so let's say we're going to we'll make it easy, and we'll send this little positively charged particle into that magnetic field. Okay, first of all, it's moving perpendicular to the magnetic field, so that's an important idea. And so as it moves in that magnetic field, it's going to experience a force. Okay, and the direction of this force is followed by your right-hand rule. So let's say our particle is moving initially this way. Okay, so he's moving initially horizontally. So fingers be the magnetic field, go into the board, do it with me, and then your velocity to the right, and you should have your palm facing up. Okay, double check. So into the board, so your fingers are going into the board. Your thumb should be pointing to the right because it's following your magnetic field, or your velocity, the velocity of your object, and then it should be being pushed up. So what happens is this little particle here gets pushed in the upward direction a little bit. He gets pushed up. So now he's going to curve a little bit. See that? So redrawing it a little bit. Now he's moving. Do you see how your particle is now moving up and to the right? Okay, so same idea, do right-hand rule. Our magnetic field is going into the board, so our fingers are going to go into the board. It's moving up and to the right, so your thumb should be pointing up and to the right, and you should have your palm pointing up and to the left. So this guy is being pushed this way. So the green arrows are in the direction of the force. And so now he's going to follow this path. And if we keep repeating that process, fingers into the board, thumb pointing in the direction he's going, and now our palm is pushing him further this way. Are you starting to see that he's starting to make a circle? Okay? So we've got two ideas kind of colliding here. We have the force equals QVB that we had before, but that force is causing it to go into a circle. And remember from a long time ago that when we had circular forces, we went and had mv squared over r. And we had a centripetal force. So these two forces are actually equal to each other. So the QVB is going to be equal to the mv squared over r. And these v's are the same velocity. So one of these is going to cancel out with one of those, and you end up with QB equals mv over r. So you do need to know the mass of your particle and its charge. You should be able to get that from these equations, from the two equations together, the QVB equals mv squared over r. I would really prefer that this is a derived formula, and you know me and derived formulas, this is only good in one instance, so be careful with that. One of your pretest questions asks what's the frequency of that circular motion, meaning how many times does your particle go around in a circle per second. Okay, so his velocity is his distance divided by his time. That's like what we learned a long time ago, right? And so what is the distance that he travels? He's going around a circle, so the distance he travels is going to be the circumference of the circle. So it's 2 pi r, that's the circumference of a circle, divided by how long it takes him to go around once. So far so good? So this is in meters per second, and this is still meters per second. So this is how we can relate the velocity to the circular motion itself. And so if we solved for how long it takes him to go around once, okay, so the time is going to be equal to 2 pi r over his velocity. And we call this time here, the time to go around once has a very special time. It's called the period. This is going to come into play when we do simple harmonic motion later. So the period is the time to go around once. The time for one cycle. Okay? Time to go around once. And there's a very interesting relationship between the frequency and the period, because if you think about it, the period is the time for one cycle. So our period is the time for one cycle, time per cycle, and our frequency is our cycles per second. Are you starting to see a relationship here? So our frequency is 1 over our period. So it would be the velocity divided by, because if we just flip this over, 1 over it, velocity divided by 2 pi r would give us our frequency. Okay, so now we're going to put all these ideas together in one problem. Here we go. So here we're told an electron enters a magnetic field of 0.75 teslas with a velocity perpendicular to the direction of the field. That just says we can use our QVB. At what frequency does the electron traverse a circular path? So it kind of looks like we don't have enough information, but let's see what we can find out. Okay, we do know that the force on it is QVB, which is the same thing as our mv squared over r, is our centripetal force. Okay, remember our magnetic force, that's how we say it, FB, the magnetic force, or the force due to a magnetic field, is going to be equal to our centripetal force. Okay, so then we said that the frequency is equal to V over 2 pi r. That's what we figured out before. Okay, our frequency is going to equal to our velocity divided by 2 pi r. So our velocity is going to be 2 pi r f. So all we did was rearrange this equation so it said velocity equals. Okay, and we know that one of these velocities in our equation here is going to cancel out. So this equation is going to become QB equals mv over r. So see how we said here our velocity is 2 pi rf, right? I know, you're like, how am I ever going to figure this out? It's what do I know, what can I figure out? What do I know, what can I figure out? And you didn't know this definition of frequency before. You didn't know that the frequency was one, how many times around a circle it's going to go. So now you know it, and you can do this. So QB is equal to m. Okay, now we've said b is this, so we're going to substitute everything in here for v. 2 pi r f over r. Now, do you see in our problem they didn't give us the radius of the circle? But guess what? Look, our r's cancel. So QB is equal to our mass times 2 pi times the frequency. And do we know the charge on our particle? We do know the charge on our particle. It's 1.6 times 10 to the minus 19, so that's Q. Do we know our magnetic field, B? Yes, we do. It's 0.75 Teslas. There's B. Do we know the mass? Yes, we do. 9.1 times 10 to the minus 31 kilograms. 2 pi is a constant. So the only unknown we have at this point is F. And so when you solve for F, you should get our answer of 2.1 times 10 to the 10. And then the unit for frequency is cycles per second, which we've renamed. You know, when you name something, when you figure something out, you get it named after you, so it gets named after Mr. Hertz. 2.1 times 10 to the 10 hertz, or cycles per second. That's what a hertz is. So in our problem, we weren't told the velocity, and we honestly didn't have enough information to find the velocity because we didn't know the force. But it worked out okay because our velocity, we had an expression for it. We weren't told the radius, but that worked out okay because the radius cancels. So don't freak out. Moral to the story, don't freak out just because you don't have enough information. You don't have enough information, because a lot of times that information will kind of reappear in different ways. So continue to ask yourself, what do I know? What can I figure out? What do I know? What can I figure out? And remember, we got this because the frequency was the inverse of the period. And then our period was the time it took to go around the circle. That's where 2 pi r came from. Around the circle once. Okay? There you go. We will see there are a couple of others like this on the pretest, and expect this is like the hardest problem on the test. And so if you can do one like this, you are good to go.